of the first presentation, but we will have also people that are registered will attend later. Sorry. They will be part of this group, and they are a few master students. 28% is our PhD. Then we have 44% are researchers and some other few professors and so on. Within this group, if I can go further, there are the most of people are not under Better 2030 umbrella, so that's an opportunity to show those people about this initiative that is covering a lot of research. And in the afternoon, we will get 35% of participants will attend the afternoon session with the hackathon session. So I hope that this will be successful. Okay, so thank you very much. So now I'm leading the floor. Can start the first session. And Marcel Mios is already here. So thank you very much, Marcel, for his very well-known person. He started working in several companies, and Umicore mainly in working in materials. Is leading a lot of activities on materials from Emiri and others following, and up to now is also chairing the working group 3 on advanced materials of Batteries Europe, and he has a well-known experience on recycling, and so we are very proud to have you here giving us a lecture on what is going to be done in this field. So thank you very much, Marcel. The floor is yours, and we are proud, happy to hear about you. By you. Thank you.
Thank you, Silvia. I'm sharing my screen. Is it okay?
Yes, I can see it well. Thank you.
So good morning. It's my pleasure to be here and to give you a state of the art of the present recycling, and with a particular focus on direct recycling that we are going to discuss. So what will be the program of today? I will show you first what the present battery market is and how it evolves from linear to circular. We will have a look at the battery recycling market, the numbers. We will have a look at the revised EU regulation on batteries and the impact of that one. To come to what we are doing in Battery 2030 Plus on direct recycling, and to compare our activities with traditional recycling processes. Show you also very shortly what internationally is done on direct recycling, and finally how we come in Battery 2030 Plus from calls to projects. So looking first at the recycling market, at the battery market. Battery market is expected to grow about 33% per year and to reach 4,700 approximately gigawatt hours by 2030. However, we have seen in 2024 quite a lot of delays and market weakening in that battery market, and I believe that we should adjust a little bit the numbers of 4,700 gigawatt hours by 2030 plus to rather 4,000 gigawatt hours by 2030. The market is mainly Chinese with 50% and heavily and principally dominated by electric vehicles. We see a clear tendency from linear to circular economy, and four R words are dominant in the present market. That is reduce, reuse, recycle, and recover. We see quite a lot of recycling activities for active materials, for cell and packs. We see second life appearing. We also see shared mobility, etc. So important is that circular economy is coming. What does that mean for the battery recycling market? We expect roughly 400 gigawatt hours to be recycled in 2030, and that corresponds with roughly 2 million tons on world level. Europe represents about 25% of that market, so roughly 130 gigawatt hours in the EU, corresponding with about 600,000 tons to be recycled by 2030. In 2040, this is expected to become 1,300 gigawatt hours on world level, meaning roughly 6 million tons. Again, with Europe, 30%, 220 gigawatt hours to be recycled, or roughly 1 million ton. It is clear that in the beginning and in the first years, that recycling market will be dominated by battery scraps, battery manufacturing scraps, and they are going to be the main feed in the next 5 years in the recycling market. What are those battery manufacturing scraps? These are cathode scraps, electrode scraps, faulty cells, and on average, production scraps representing roughly 36% of cathode material, 22% of anode material, corresponding 18% of copper collector, 10% of aluminum collector, and the rest is electrolyte, graphite, etc. So the first years will be, the main feed will be battery manufacturing scraps. What is the impact of the revised European battery regulation? The new battery directive requires low carbon footprint batteries, much stricter policies on critical raw materials, and high quality recycling of batteries. We see increased targets on recovery, on recycling efficiency, and minimum recycled material to be reintroduced in the cells. For instance, in 2031, the lithium to be recovered increases from 35% to 80%, and for the cobalt and the nickel and the copper, we have recovery targets of 95%. Recycling efficiency is going to increase from 65% today to 70% in 31, and for the minimum recycled material content, evolving from 6, 6, 16, respectively for lithium, nickel, and cobalt, to 12, 15, and 26%. So overall, 100% increase in the use of recycled material. So what are we doing in Battery 2030 Plus on recyclability? As you know, the CSA Battery 2030 Plus tries to reinvent the way we develop ultra-high batteries of the future, and that by an accelerated discovery of new materials, new battery concepts, introducing, like Sylvia said, new smart functionalities like self-healing, like sensing, etc. And that at the same time making sure that all those systems are manufacturable and recyclable. What we promote in Battery 2030 Plus is direct battery recycling as a key strategy to maximize sustainability and to improve our geopolitical independence in the whole battery value chain. So what is traditional battery recycling? There are three types. There is hydro, there is pyro, and there is mechanical. For the traditional processes, in hydro, the materials once collected are crushed, are shredded, and are first undergoing a lot of physical separation steps. That brings us to black mass. That black mass can be sold, traded on the market, and that is mechanical recycling. In hydro, this black mass is further treated by leaching, by precipitation, by electrowinning, etc., refining in general, and that leading to new secondary active materials. Pyrometallurgy, in fact, does not use that shredding process. The cells are going immediately in high temperature furnaces, and this gives a rise to a white alloy, and that white alloy contains the nickel, the cobalt, and the copper. There are slags, and those slags contain aluminum, manganese, and lithium. Those slags are also treated to recover the lithium, and those products are going into further refining and followed by traditional calcination and reuse in the system. What makes direct recycling different? We try to combine that with Second Life. And that starts with data collection on the battery packs, based on sensor information, based on label information, based on the future battery passport information. And then we try to dismantle those battery packs to respectively modules and then cells. And at each of those levels, we are considering the reuse in Second Life, repurposing in Second Life, based on fast state of health determination. Important is that automatic disassembly process from packs to modules to cells, and then it continues with the smart opening of those cells and the recovery of the individual components of the battery cell by techniques that I will show you later. So we open the cells, we try to recover almost all the materials from the cells by special technologies. We recover the cathode material, we recover the anode material, and if possible, the electrolyte. We do reconditioning treatments on those materials, and we are reusing the materials as such in further new cell processing. When this is not possible for purity reasons or whatever, an option is to transform those materials to precursors or to really steer them into full recycling. So what is the key? Direct recycling is recovery of the components and trying to reuse them as such in new cell manufacturing. Improving the recovery rate, decreasing the energy consumption, and lowering in general the carbon footprint. So Important for direct recycling is first data collection. We are doing that in small carbon footprints, if possible in decentralized processing. The automated pack disassembly through modules and through cell level, investigating wherever possible, the reuse and repurposing, and stimulating and developing automated disassembly to individual components. Those components are reconditioned, are transformed into novel materials to be reused. Important here is that we try to come to lower energy consumption, that we improve the recovery rates, that we have a more sustainable process, but that needs also international collaboration, and that's what we are trying to stimulate. So what are the priority actions? First, selective separation and recovery of the materials, cell opening based on cell cutting or mild cell shredding, electrode separation, recovery of the materials. Technologies for delamination are used, for instance, ultrasonic or float flotation. Recovery technologies on the materials that are recovered. And for the cathode, this means relithiation. That also means a reinstallment of coatings on the materials. Cathode upcycling, that means that adjustments have to be made on the compositions to make them updated in the present compositions, and having a good look and a serious look at the impurities, because the impurities are of utmost importance for the novel for the reuse. Finally, the materials will be validated in automotive and in stationary applications. We have translated that in a roadmap in Battery 2030 Plus. We have a series of actions in the first 3 years. We have actions in the medium term, 3 to 6 years, and we have finally in the long terms, at 10 years, hopefully a full system for direct recycling installed, developed, and qualified. There is a lot of international work done on direct recycling. And important, for instance, is ReCell in the United States with Argon. And they are doing exactly the same thing as we are developing in Battery 2030 Plus. Maybe a little bit broader even than that we focus on. Special attention also to electrolyte recovery, the same actions on electrode separation, recovery of materials, a lot of international work on binder removal from the cathode material, on the cathode relithiation, on graphite recovery, and on cathode upcycling and evaluation of the impurity impact. Direct recycling is especially important for low-value battery compositions, for LFP. And we see, and here direct recycling is really the technology of choice for LFP. We see that then we will have, I believe, a speaker from Kiburs on LFP direct recycling. There are many European projects on direct recycling of LFP, and there are startups like Cell Circle stepping into these technologies. How do we, with Battery 2030 Plus, come from ideas from the roadmap to projects? We do that in the context, like Sylvia already explained, in the ecosystem of battery research. And the ecosystem of battery research is European Battery Alliance, EBA, 250. We do that ourselves in Battery 2030 Plus. The ideas go into the European technology platform and innovation platform Batteries Europe. From there, they are uptaken in the BEPA, the Battery Alliance, and we have introduced direct recycling in Batteries Europe, in the integration of secondary raw materials. We have integrated direct recycling from Battery 2030 Plus in the battery partnership, in the strategic research and innovation agenda. And this has led to a series of new projects on direct recycling, renovate, revitalize, and reuse. We will hear more of them later in the morning. And if we look at the present coordination activities Battery 2030 Plus, there are about 18 or 19 projects that are coordinated by Battery 2030 Plus on functionalities, on surface integration, on materials discovery, on manufacturability, and on raw materials and recycling. On raw materials and recycling, we have, as said before, renovate, revitalize, and reuse. But we also have for the raw materials side, Kikero, streams, and lithium for life. So that was my introduction. Hopefully, this will be further explained in the projects that are going to be presented next in the next presentations. Thank you.
Thank you very much, Marcel, for this very nice and clear overview. I guess that we can now have the presentation from the companies, and then if there are some few questions, we will collect them. So I hope you can stay and answer later. So thank you very much. So I can give the floor to David Flaschenträger, who will present us their activities. Can you? Okay, thank you, David. Perfect. That's great. So you did everything by yourself. So thank you again. Please go ahead. Thank you.
Thanks. And thanks everyone for joining. I'm David, and today I would like to talk to you about direct recycling, how we do it at Kibbutz. Thanks to Marcel for already explaining what direct recycling is and why it's important. And so I would like to talk to you about what blenders have actually to do with battery recycling, why bigger is not necessarily better, and lastly, why care about recycling in the first place when we could fiddle around with our fancy vehicles all the time. So first things first, who are we and how did we start? So Martin Kibbutz, our founder, started basically the company back in the early 90s. He was basically a nutcase who wanted to race solar and EV races. Back then, those were not commercially available, so he had to build them by himself. And from there, he made a business, firstly making vehicles for the elderly, which since 2008, 2009 are all powered by LFP batteries. And that's important for the next steps. And now you can basically find us all over the world. So you see our best-selling product in different applications, typically with postal services ranging from, of course, Switzerland. But I think the one in the top left is, I believe, Finland. No, the top right is Finland, and top left is another Scandinavian country, or vice versa. And bottom right is Australia. So we are basically everywhere in the world with our vehicles. And what we do, except the vehicles and offering the services to maintain the vehicles, is what we call new business units. And there we have digital fleet monitoring solution, which grew out of our vehicles and our vehicle fleet. Battery recycling, which we'll discuss in more details in a minute. The E-Rod you already saw, a fun vehicle we produce in small series or small quantities, and the Circular Economy Symposium, which is typically held once a year. Next time will be held 6th of September here in Switzerland in our new headquarters. And so these are different topics we work on. Now, our company overall, roughly 180 people. So you see many of my colleagues in the picture. I personally was not available that day, so you won't find me. But nevertheless, yeah, we've got roughly 30,000 of our vehicles up and running, which have covered more than 400 million kilometers. So we're really providing our customers products for heavy duty usage. As mentioned before, you can find us basically everywhere in the world, including Germany, so on a small scale, but even Germany, Netherlands, almost whole of Europe, and yeah, even fancy countries no one has ever heard of. And why did we start to deal with battery recycling ourselves? We are a vehicle producing and a vehicle using company. So it all started roughly 15 years ago, I would say, when we first started to ship our vehicles to the Swiss Postal Service, the Swiss Federal Postal Service. And there, when the contract was signed, it was defined that after a period of 7 to 9 years, we will buy back the vehicles. And back then, we didn't know what to do with the old vehicles. But quickly, we realized that they were still too good to be thrown away. So we started to refurbish these vehicles. And in many cases, the battery is still perfectly fine and could be used in a second application or could be brought back to the road again. But in some cases, the battery would be not so good anymore. So for us, the threshold for a battery to be used in a mobile application is roughly 85% SOH, state of health. So if the battery is has an SOH of lower than 85%, we would not use it in a vehicle anymore. So then the next best solution would be, okay, if we can't use it on the road again, let's use it in stationary energy storage. So we started roughly 10 years ago to make stationary energy storage systems by ourselves. In the meantime, we have outsourced that, but that was a way to reuse the batteries once again. But every once in a while, there would be a battery that would be even not good enough to be used in an energy storage system, in a stationary energy storage system. So what would we do with these batteries, which piled up over the time? And back then, there was only one battery recycling company in Switzerland who used a pyro process. So Marcel just 20 minutes ago explained what the pyro process looks like. And our founder, Martin Kiburz, was like, there's absolutely no way we are burning our batteries. We have to come up with a better solution. And that was the initial starting point for the battery recycling initiative at Kiburz, which started roughly in 2017, 2018, when Olivier Groux, at that time student at the University of Zurich, came up with an idea how to disassemble battery cells and how to decompose the battery components into single chemical compounds and single components. So from there, we derived the first generation Liberty facility. Liberty is the name of our direct recycling facility. And it's comparably small. So compared to a shredder or to a shredding facility, it's super small in footprint. It requires super little energy, but also comes with some drawbacks. We'll come back to that later. And we commissioned that facility back in 2020 and received the operating license back in 2022. And since then, we are a recognized battery recycling company in Switzerland, where we can mainly focus on our own batteries, but also started to collaborate with other battery recyclers, mostly to get rid of their LFP stocks. Because as Marcel already pointed out, for LFP recycling, direct recycling is probably the way, because from an economic point of view, it just does not make sense to recycle LFP cells in a hydro or in a pyro process. So that's why battery recycling companies reach out to us, and we try to help them get rid of their LFP stocks. So what's the difference, and what's direct recycling maybe on a more abstract level than Marcel just pointed it out? We are often asked to explain our process to people who are not familiar with batteries at all, that do not know what's the difference between a cathode and an anode. What does coating mean? What's a current collector? What's a separator? So we always try to show it in a more real world way, or in a way that's a little bit easier to comprehend eventually. So if you imagine that this basket full of vegetables represent a single battery cell composing of different components, then what traditional battery recycling looks like is pretty much this. So you've got a blender, you put everything inside, you blend it, and your product is a smoothie, or as the battery industry calls it, black mass. So we heard that today already. So that's a shredder up in the right that can shred entire battery modules. So these are cells from the automotive application, comparably large. And the big question then is, how do you make a new battery out of this material that you see on the right-hand side or on the lower picture? So it's quite energy intensive. And I don't want to say that direct recycling is a substitute for traditional battery recycling, because it's not, because traditional battery recycling, shredding, hydro, pyro, they have some really good advantages. So these processes are super versatile. They are well-known, robust, and you can make use of existing infrastructure, namely the metallurgy. And the end product of these processes are typically precursors that can be used to formulate new batteries and new battery materials. Because if you imagine in a fast-paced industry like the battery industry, where chemistries literally change on a monthly basis, you do not want to recycle a 10-year-old battery and regenerate it to generate a new 10-year-old battery, because technology has moved forward, and a battery that was new 10 years ago is just not market ready anymore. You can't sell it. You won't find a customer for a battery that's 10 years old, even if it was brand new. So the traditional battery recycling still has definitely its benefits, but they come at a cost. So I already mentioned that it's quite energy intensive to make a new battery out of these materials or out of black mass. These, especially the post treatment, so the metallurgic part, the hydro or the what's sometimes called refining part, they require quite large investments. And here we are not talking about millions and not tens of millions, but literally hundreds of millions of euros or dollars. So these are super large facilities, and to become economically viable, they have to run on 100% capacity, basically 24/7. So you have to have large amounts of materials to basically get your factory up and running. And that leads to a centralized approach typically, which requires then a lot of transport and a lot of emissions coming from the transport. And you probably heard in the news that most of the black mass is shipped to South Korea, or eventually China, Indonesia, other places, mostly in Asia, because there's just not so much refining capacity, not so much battery value chain in Europe available right now. And that becomes a real big problem if we are talking about low-cost chemistry, such as LFP, but also sodium ion and what's around the corner, because the main driver for these chemistries is basically the low price point, and the low price point comes from cheap materials. And if the materials are cheap, you cannot afford expensive processes to gain cheap materials. The economics simply won't work. from a technical point of view, there's absolutely nothing wrong to put a LFP battery into a hydro process. But every accountant is going to tell you that it's not going to pay off. And that's the main issue here with these low-cost chemistries. So what do? We start again with a basket full of vegetables, and we cut them in slightly bigger pieces. And with, in that case, toothpicks and a little bit of fantasy, you can reassemble something that's eventually not exactly the same thing, but it's similar. And we could show that in the past. Back in 2022, we were able to show that from the materials we get out from our process, and that's what a battery cell looks like after going through our process, we can make a new battery. It's not high performance. It was not a developed product. It was just a proof of concept and to showcase that in principle it's doable. And how the process looks like, I would like to show with that brief video. Some of you might already know it. So that's the facility which is literally standing 20 meters behind me. So first, the cells that mostly stem from our vehicles, they are opened by a traditional thawing process. And then by using compressed air, we eject the electrode pack out of the casing of the cells. And in the next step, which is partially manual, we start separating anodes from cathodes. So we got anode in one bin and cathodes in a different bin. And we never mix these materials. And that's very important because in this way we can just assure a very high material quality with little to almost no contaminations. And in the next very short video, we kind of show what happens if you immerse these electrodes, being anodes or cathodes, depending on the cell chemistry and the binder system. You immerse them in a solvent. In our particular case, it's deionized water, but in some cases we have to use other solvents. And as you can see, quite quickly, you can simply detach the coating from the current collectors. And the really cool thing about this is that you need little to no chemistry, little to no energy, and you end up with a very high qualitative product. So in our case, with an example from our vehicles, where per vehicle we mount 8 cells, which are in total around 23 kilograms, we can recover more than 90% of the materials without the use of any chemicals and without the use of any large machinery. Of course, mainly the recycled LFP, followed by graphite and copper, slight amounts of or smaller amounts of aluminum and plastics, and yeah, that's how we all started. And brief look back into history. So I mentioned that back in 2017, Olivier started the process. So here he's still young and fresh, and a few years later, back in 2023. Still fresh, but grown a little bit older, received once again a prize for our process. And back in 2024, the reuse project that was already mentioned started with collaboration of keyboards. And we started the next phase. We'll skip this. And started collaboration with back then Vitesco Technologies, who has now merged with Schaeffler. Schaeffler, for those not familiar with it, is a automotive supplier, annual turnover of about 25 billion annually. And they are developing now or helping us to develop and bring our product to market because they see it as a viable long-term business opportunity and one major step to fulfill their circularity or environmental goals, basically. And with this, I would like to conclude and just to give you some key takeaways. Direct recycling is a promising complement for established battery recycling. It's not an alternative. We will not see that all batteries from all applications will go into direct battery recycling. This will simply not be, it will not be possible. Where direct recycling is in particular suitable is production scraps. We heard already that production scrap make up the majority of all materials that need to be recycled from batteries at least until 2030, eventually 2031 or even 2032. It's in particular well suited for large format cells, and it's basically the only way to recover low cost chemistries in a good fashion. And lastly, it allows to scale through number of facilities instead of size or capacity of single facilities. And that comes with a lot of benefits, and I think it's very important to emphasize on. And with this, I would like to thank you for your attention.
Thank you very much. Sorry, I got the microphone off. Thank you very much for very inspiring and very interesting presentation. I want to give the floor now to Arne Seeger from Stena. And then we will come back with some questions that I see appearing now in the chat. So thank you. Please still use the chat for questions, and thank you very much. Thank you very much, Arne, for being here, you too. And so please, if you can just give us what Stena is doing in this field and present your company. Thank you very much.
Thanks, Sylvia. I hope you can hear me well. And
very well, thank you.
My name is Arne Seeger. I'm the last speaker in this early session, and I think then we transition into the next item. Thank you, David, also for your presentation. It was really nice. I'll jump in a second. Let me try to share the screen and see if that will work. And you let me know if you can see by clapping your hands.
Yes, now it's visible. Thank you.
Fantastic. So, Sylvia, having you from Italy, there is actually a Stena in Italy as well. It's doing recycling of mostly WE materials, so waste electric appliances, but some batteries is coming in. We have a storage right now, a certified one, and it's increasing. And we will see it on the map. So I have shortened my presentation since we're a little over time, I think. And I will see if I will go to the next slide. Let's click here. Here we go. So maybe you've seen us. Stena is a big company. This is just for you now. Join me for a short ride. I will give you a very short introduction to Stena and a much longer on, a little bit an overview of what is a classic recycler doing, because I do believe in direct recycling, but today there's volume that we cannot direct recycle, so we need to rely on the old state of the art, and that is what Stena is doing. But first things first, short introduction. This is an overview slide. I won't go into it now, but Stena is a big company, is the takeaway. It's a family-based company from Sweden, and we do have actually 3, I think, at the moment, facilities in Italy. One is in Carpi. The one in Carpi has the battery part. Here you can see it.
How are you?
On a European map. So I'm sitting in Hamburg. I'm talking to you from Hamburg right now. You don't see a dot there, but I'm somewhere in the middle of the battery activity, you could say. What I want to show you, these 2 other points, they are a bit bigger, and this is what I would like to go into. So what does Stena do, and how does a classic recycle, let's say, tackle the battery problem today? So we split it up into an overview, and we've seen this from Marcel before. So it's actually quite interesting that these graphics, they are usually circular. I want to make it a little bit more linear again, because it's easier to show you. So if you start with collection storage, and this is a lot of legislation going into that to do it right, it's available, and maybe on the bottom right, the color code there. You can see this is for European Union, and I want to show you what is available and what has low availability and what is not really available. So the first thing that always comes to mind is, hey, we could test this. This might have a value. It goes for LFP, goes for NMC, any kind of chemistry, could be a battery still. And then it's a problem, because on the pack size, the recyclers cannot do much. That's reserved for the OEMs, because you have to open a pack to test it as a recycler. And then the next thing is, there's also, if you open it and you have some little faults that you could repair, there's nearly no one that could do REACs, meaning repair, manufacture, or refurbish, available right now. That would be a workshop network that is trained up by the OEM with connectors, with tools to read out data, and then also with sealants, new screws, all the things that are hardly available right now. You could go another way, and you could go downcycling, which means you go from a car battery, for example, traction battery, down to an ESS battery that has a lot lower C rates and a lot lower power requirements. Yeah, we do have that. I paint this in yellow now because we had that actually. They are dying right now because the new LFP batteries from China are cheaper than downcycled packs and modules. And for cell, it has never been available. So for cells, they have always been sold overseas, usually to Africa or China. They have never been recycled in the EU in a downcycling way. It was always modules and packs. So what does that leave us with? And you see the color here. If you have charged batteries, they become end of waste. They're collected. They go to through a dismantling route into some form of taking the energy out. That would be the upper one. Electric discharge is kind of the European way, I would say. Credit to Umicore and others. Thermal pretreatment is a big thing, Acrec, for example. So you could use pyrolysis to get the energy out, use the energy for your heat, and discharge the battery in that way, make it shreddable, let's say. And then the lower part, haven't seen it in the EU very much, but in China, that's number one. You submerge, you put them in a saline solution, and you wait a week or so, and then you get a discharged battery, quite corroded as well. That gives you some form of discharged module and cell, and those you can then again either do a pyrolysis to get the binders and the electrolytes out and tread. You could also do, and this is the Stena way here, and it's maybe you've heard of Duesenfeld and seen a video. This is I would say, current state of the art. It's at least the newest addition to the traditional ways. You could use vacuum to keep the temperatures low to avoid HF formation, or you could go submerged shredding, so go into water again. Is for example a Lye cycle or an EcoBat way that you could see in Germany, for example, 2 plants, and all of those are fully available. Now, when you look at this in the middle, I'm kind of omitting the direct recycling. And that's because I'm trying to tackle the industrial sized things here. And I know that there is a good place for sodium ion and LFP for direct recycling, for sure. So consider this the future for NMC and the current for NMC and LFP. Those processes leave you with black mass and others. Then traditionally, we can put this in as we heard earlier, in a kiln. We could actually put batteries directly into, if they are small enough. We can't fit a pack, but if we have modules and cells, we can usually go into a private process directly. For payability reasons, all the recyclers will try to get their black mass into a spec. The spec is then much more controlled. Organics needs to be lower, go directly into hydromet. And here you see the first yellow appearing again. So we have an issue in Europe. We can take the metals, the metal part of the pyrometallurgy, put them in hydromet, or we could sell it off as alloys and produce different alloys from it. If we have a hydromet, these metal salts are just technically great. So they go into a PCAM process, and that generates the metal salts needed for chem production. Problem is, these two we don't really have in Europe. So some naming convention that we use in the industry is this we call preparation. The middle part here we call pre-treatment. The latter part here we call recycling. It's just the hydro and pyro processes. And production of new batteries would then be PCAM and CAM. And the production process, that's what's missing. So if you look at EU, US, and Asia, you get everything in Asia, but you don't get everything in the EU and the US. So this is an overview. I spent a lot of time on this slide, and maybe there's a question back to you, Sylvia. Are these going to be available as PDF or something? So you could zoom in or do whatever with those slides.
We will record the workshop, and this will be available. So if you want to share the slides, we'll be more than welcome, of course.
Super. Thank you.
Thank you.
The Stena part we do, you can see then Hydromet is our external partners. That's the outgoing. So we do everything from collection through what we call the battery center process. It's dismantling discharge, electrical discharge, to the recycling down to black mass. That's where Stena stops. That's a quite typical European scrap recycler tackling the lithium-ion battery problem. And here in this overview, you see the different parts we take out. So the graph before was really about the cobalt, nickel, and lithium. maybe graphite. And this is then all the other things which are really interesting, especially the copper. You might be surprised that in 2022 it was all about nickel cobalt, but now with the prices today, the copper foil has placed the third biggest. I think it's just beaten by cobalt and nickel, and cobalt is going to be beaten by copper soon in terms of value in a recycled battery. This is how it looks. So you get a bottom left, you get a little, truck storage. You put them in storage containers for safety reasons. You dismantle discharge in a smaller building. You go into a bigger building. One is basically an inbound storage, and then you go into a feeding area, into a wet line. Wet because you take the electrolyte out in that area, and then you go over to a dry line that also accepts production scraps. So we talked about cathode and anode foils that could go directly into the dry line. And then you have an outbound storage. This is the facility we run in Halmstad. It's southern Sweden. And it looks like this. And I want to show you some pictures now, so you get an impression of how big it is. And this cost 30 million euros as an investment. What you see here, all these buildings, and on the picture before, the layout internally. This example is from the back, so you can see the storage as we installed it now. And they are all separated. It's really a fire protection measure, because when you store a battery that's still charged before discharge, you might get surprised on a Saturday night. If you move into the hall, the wet line, it will look something like this. This is a vacuum shredder, vacuum sealed. And then on the left that you can't see, but all the pipes are going over. Electrolyte is evaporated and then condensed in chillers. And it's quite a big installation for the electrolyte treatment afterwards. The dry line, mainly basically delamination and sorting line for copper, aluminum, and others. The Stena line looks like this. And yeah, you do get aluminum, steel, copper, all separated from each other. And then the final product that we want to keep the most clean to be inside the Hydromet spec is the black mass. For not having any internally, but close around in Finland, you have Fortum in Hiawatha. It's a Hydromet process in Europe. It has begun to operate, but it's not fully utilized yet. Same as many plants in Europe, actually. So they use I think it's a normal approach, solvent extraction with sulfuric acids. And then their targets are manganese, but mainly nickel and cobalt sulfate. Leaves us with the last part here. And I want to give you a short overview. And Sylvia, stop me when I'm running over time then. Of challenges that we have, and that probably everyone in this industry has. So we do have an overcapacity of recycling because the market didn't come as expected. We saw it from Marcel that 2030 expectation gigawatt hours is down. I would say it's down like by 50%, not by less than 20% in my view. But then I'm German, and we have lost more than 50% of the announced capacity in production. Way more, actually, like 70% is gone. And then the second life or the reuse or the end of life market, all that is much smaller than anticipated 2025, and that will carry through to 2030. So we are believing that it's kind of 5 years delayed, not 1 or 2. We do have however, we do have very low Hydromet and PCAM capacity. So there is a possibility to enter the market, and many are doing that right now. So that's coming. But we have a huge overcapacity for shredding and separation and pyrometallurgy. So there's a fight over volumes. And on the bottom right, you can see, I'm still a bit German there, but you can see the different stages, and you can see how much we have overcapacity. And actually, in Europe, it's not that bad. It's actually worse in Asia. And we can see that by getting requests every day to send something, send batteries to Asia, send black mass to Asia. Black mass and batteries that we don't even have in Germany or in Europe. Next challenge I want to present to you is what I call it the semi-legal export. And that is if you take black mass, but it could be a battery too. It's mostly black mass. It is quite flexible. It moves from Hungary, from Germany, from Holland over to countries like Singapore, South Korea, Japan. Sometimes even directly into countries. Then it becomes very semi-legal. Why is that semi-legal? Because people are using non-hazardous waste codes, or sometimes they ship it as a product and not as a waste. And the European Union is trying to make that more clear that this is a hazardous waste and needs a proper a lot of documentation. From those countries and from Europe into China is hard, but from those countries to China is easy. So then it's a secondary flow going from those countries into China for the final treatment. So it will be very, very hard to see a PCAM facility fill up in Europe because they have to compete with the existing market in China, has a better cost structure than any European effort. Next challenge I want to show you is more visible. It's a cell module pack on the left and a cell to pack on the right. And I think without saying anything, you can see what a recycler having their hands on a battery faces here. I mean, you can have between components that you can't really see on the right side. You have 400 or 800 volts. Both are quite deadly if you touch the wrong things. If you put a tool down, the tool will melt on the right and on the wrong spots. So quite hard to dismantle, quite hard to open without getting into, let's say, quite a lot of trouble. And final slide here. This is the overview. Won't go through it. And I've added one more thing in the end here, the chemistries. I didn't have a good picture for that, but you can see that we struggle with a lot of things. And if you, as young research, are researching into the current industry and want to help out the established recyclers, these are things that we really need help with, these four here. And chemistries, that's more the ones coming. Right now, this might be 1 in 1,000 of the batteries incoming. And we put them aside and we store them for indefinite years and wait. But in the future, we need to solve that. And maybe then final few words on potential solutions. For recycling overcapacity, it will be solved by time. Semi-legal export, it might be solved by legislation. I don't believe that because it hasn't worked so far quite well. The cell to pack, we are working on it actively. There's a lot of research going into cutting technologies, and for chemistries, it's per chemistry. There are solutions, and they are being developed. So thank you very much for listening, and it was a pleasure to be here with you.
Thank you very, very much to you and all the speakers for the very nice and clear presentations. We have some questions, so I can. One of the question is if it is possible to visit your battery recycling facilities, and it's could be very interesting, not only for the youngest. So this is for both Arne and David. It depends, maybe this is the answer.
David, do you want to start?
Generally speaking, they're very open.
We can hear you very low, maybe, yes.
Sorry for that. Generally speaking, we are very open for visits. Right now, there's a group from the University of Saarland behind me, and they're waiting for me, so I'm a little bit short of time.
Yes.
But yeah, generally, we are very open to that.
Super. Thank you.
Yeah, and comment from Stena, it's actually, if you want to go, the facility that I showed you in Halmstad, that is connected to a facility, the Stena Nordic Recycling Center. You can see non-ferrous and ferrous recycling, plastics recycling, all in one spot. It even has a visitor center. It's kind of the one we want to show. So yes, you can register there, and then you get even a tour for free. Usually you get a helmet on, and then you can see a lot of different waste processes when you go there. Only you won't meet me there because I sit a few hundred kilometers south of that. But there's fantastic colleagues that can show you around for sure.
Thank you very much. I take a couple of questions as we have 5 minutes here. This question can be for all the speakers, also Marcel. Could we use old battery materials and upgrade them with coating or additives? Please, if somebody wants to answer, please, Arne, if you're here. I don't know if Marcel also is here.
Out of my expertise, but I've heard that
Okay.
It's possible. Yeah, but it's not a qualified comment from my end.
But this is the purpose of direct recycling, to recover
Exactly.
the materials and to look at them, look at the crystallographic structure, look at the coating, look at the composition, adjust the composition. This is the upcycling part, and that means restoring the composition, restoring the coating. Yes, that is what we try to develop in direct recycling.
Thank you. We have one question for keyboards. How about chemically sensitive active material chemistry like moisture or other factors? High nickel in NMC, for example, do you evaluate the process for all chemistries?
Yeah, definitely. So we don't do it in a productive way, so we do not treat it in masses, but we work on it in a lab also within various research projects. And there's two ways two ways we work on that. So the one is it works surprisingly well in many cases, even with water. Even if the binder system is PVDF based, that does not necessarily mean that that water cannot be used as a solvent. So it does not dissolve the binder system itself, but it overcomes the adhesion between the coating and the current collector. So that works surprisingly well. And when it comes to nickel-rich materials that leach out in water, for example, we do use also other alternative solvents, green solvents, environmentally friendly solvents that do not lead to this leach out of the NMC material. NMC is in particular prone to the leaching process, but since we are focusing on LFP mainly, it's right now not our main concern. Let's put it like this. And
Okay,
LFP just doesn't react with water.
Yes, of course. Thank you. So there's a last question for Arne. Let me say, this one is, you say solid state batteries cannot be shredded due to fire and explosion, but solid state batteries should be safer than traditional ones with liquid electrolyte. So what matters here?
It's the same with the cell to pack and cell to chassis. It's much safer in a car in the lifetime. Only for the recycler, it's unsafe. We have the problem that a little bit of metallic lithium will stay not in the cathode, but on the anode. If we shred this and we have a little bit of moisture, or we will have a exothermal reaction in the shredder, and it will pretty much destroy the shredder from the inside quite quickly, actually, because we will have HF formation also, depending on binders and electrolytes used. And all this can be solved, I think, in the future. But if you discharge a battery, it's always a little bit of lithium staying. And if it's a lithium metal anode, then it's a big problem. This isn't solved for us, but I think we might find a way, and maybe direct recycling could play a role here as well. I'm not sure. So this is so far into the future. I mean, we haven't seen those batteries yet. We have seen the first sodium ion, and we have seen a lot of all the different chemistries like high nickel, like 9.5.5 chemistry. So this is more the current problems, but yeah, it's very, very critical for us with these solid state batteries of the future that we think we might see quite beginning of the 30s, maybe coming back from the first broken down cars.
Thank you very much. This was very interesting point of view. I have one very last question for everyone, because there's a sort of competition between, let me say, Second Life and recycling. The two are in competition. It's a sort of challenge. What do you feel? Is it, for example, in the case recycling will be much lower cost, can Second Life never be used, or there are two different way of proceeding? What about your ideas on it? Please, Marcel first, so we go as speakers.
But I personally believe in Second Life. Materials, an LFP battery, for instance, can be reused in Second Life. We promote Second Life in Battery 2030 Plus in combination with direct recycling. So I am a believer personally in Second Life.
What about you, David?
So there's a company policy, and there's my personal opinion. And my personal opinion, unfortunately, is that technologically it might be possible, but economically it's not going to play out because new LFP is just so cheap. And we saw prices dropping for more than 50% over the last 24 months. And we see now many projects who deal with second life applications, second life energy storage systems and so on, to really struggle, not from a technical point of view. They have two major issues. One is the price competitiveness. And even if you can sell at the same price, customers will tend to new products. And the second is the supply. You need, if you've got a really nice product, you're super cheap, you've got lots of customers, then you have the problem you probably won't find enough cells of one single kind, of one certain quality. So it's more an economic problem than a technological one.
Thank you. And what about your opinion, Arne?
Agree with David. It's dying. I had a presentation from Tricera. It's a company that builds Second Life ESS, competes with Asian LFP new systems, much more higher integrated, like 5 times the energy density per volume. Yeah, they said that they ended the production of putting secondary in 2024. That was the year when it turned negative. I think it's around $150 the kilowatt hour of cell price in Asia. That was the tipping point when the new batteries became better. Now they're at 78, so we are like half the price now of new cells versus reused cells, because the reuse is so hard to do. The measurements, the pre-treatment to make them in a right classification, so they are manageable for a second life actor, is time consuming. You might be able to do that in some countries, but for Central and Northern European countries, it's no way. It doesn't work anymore.
So thank you very, very much. It was, I guess, a very, very nice and interesting session of this workshop. So thank you so much. We are pretty on time. And so I give the floor to Gwen now, and she will introduce the next session. Thank you so much. And maybe Gwen is here. Thank you.
Yes, I'm here.
Thank you.
So I'm just going to take 1 second, and I'm going to shift spotlights around as we move from our industry session to our EU projects session. It just takes a second to find everybody in the list. And Eliana, you can already start putting your screens up, or your slides up, if you would like. So I'm happy to be able to introduce both Eliana Quattronone and Andreas Flegler, who are going to represent 2 of the 3 projects that have been funded by the EU under the Battery 2030 Plus umbrella. So the first project is going to be from Eliana and the project Renovate.
Okay, thank you very much. Can you see my screen?
Yes, we do.
Okay. Thank you, Silvia, for the kind invitation, and thank you, Gwen, for the kind introduction. I'm really happy to be here and share with you how Renovate wish to contribute to the recycling domain here in Europe, and also our first outcome that we are just achieving now. Renovate is built on the complementary know-how of 11 partners in Europe, of course, coming from university, so academia, research, battery manufacturing firm, which is working on LFP-based chemistry, 2 large chemical companies, but also 2 small, medium enterprise, and also a producer responsibility organization. Our mission is the development and demonstration of new, innovative, and more sustainable recycling technology that we are going to demonstrate at TRL4 for the European battery value chain by recovering and reusing more than 95% of end-of-life batteries, but also battery components, meaning, for example, metallic foil for the current collectors, graphite, and other organic components, and with a special focus on industrial side streams, the manufacturing scrap, first of all, but also the side waste, the waste side streams coming from the proposed recycling process. This will be done through a closed loop recycling strategies targeted for lithium-ion batteries based on easily implementable, at least almost net zero carbon process for low value and also high value chemistries. In case of low values, which substantially means LFP, we will develop new sustainable direct recycling strategies, and in case of high values chemistry, for example, NMC, greener and sustainable solvo and soft hydrometallurgic, with a view to at holistics and more flexible process. A specific focus will be devoted also to the treatment, a smarter integration of the side streams, especially in order to minimize waste coming from the process in terms of reuse of scraps, water, wastewater more in general, and also chemicals. We wish to maximize recycling that has been mentioned before by the colleagues is a physiological enabler of circular economy through several technical objectives, from the enhancement of recycling efficiency by improving the selective separation of the component to also have higher profitability and higher revenue by recovery non-CAM cathode active materials, for example, by focusing on direct recycling of LFP coming from, of course, end-of-life batteries, but especially scraps, because now it's what we have available. But also by developing greener metallurgical approach for the recovery of critical raw materials from the high chemistry systems with process that can be easily adapted also to the sodium-ion batteries where the same critical raw materials are included, for example, in case of layered oxides. The valorization of side streams and also the validation of the recycling process by reusing materials in the remanufacturing of new battery cells with a closed loop, of course, and being aligned to the battery regulation. All the outcomes will feed a full life cycle assessment, including the cost analysis of the process, and also a proof of concept of a digital architecture that will act as a cross-cutting digital design support systems, which will also include predictive regulatory framework models, which will help the scaling up of Renovate solution when ready and when possible. The Renovate concept is sketched here. We are collecting end-of-life batteries coming from several recycling, several applications, and also manufacturing scrap from our partner in the battery manufacturing. The waste will be, from the waste we will remove the electrolyte first removed and also recovery in order to prepare the waste for the mechanical pretreatment by high voltage fragmentation in order to pre-concentrate, the first preliminary pre-concentrate the black mass that will be made free from the fluorinated binder, for example, when present, of course, for example, by innovative technology like the supercritical fluid extraction, and have to achieve a higher purity black mass from where the graphite will be recovered through froth flotation in order to collect just the cathodic component that will undergo direct recycling in case of LFP or a greener metallurgical approach when the batteries is based on NMC, for example, chemistry, and the recovered materials will be reused in the preparation of new cells, as mentioned before. But a focus of Renovate is also to investigate the potential of inner circularity in our project by valorizing the side streams that we are collecting in our recycling process. I can just mention the reuse of carbon dioxide electrolyte coming from the supercritical fluid technology that can be tested as a precipitation agent to collect lithium as carbonate, for example, but also the transformation of low quality of organic carbonates recovered by the electrolyte in case of end-of-life batteries has valuable surfactants for new polymerization process. And of course, last but not least, the purification of wastewater and green solvents that we are planning to use and we are just using in our technologies. Where we are now, the project is built on 3 consequent phases. First, the collection of waste stream, and stated before, and now we are at level of developing and validating the single process in the Renovate concept for each component of the batteries in order to achieve the final step to validate the full Renovate circular approach. Of course, all the outcomes will feed full life cycle analysis as mentioned before, and also the digital platform. So what I have the pleasure today is to share you the main key innovation points of Renovate and also some preliminary results, starting, for example, from some innovative mechanical pretreatment that we are developing in order to achieve better materials that can be easily recovered. And I mean the high voltage fragmentation, which is not new in the mining industries, but is quite new in the battery recycling technologies. That has some important advantage, especially the possibility to add more value within the circular lithium-ion battery supply chain by achieving simplified downstream chemistry and also improved downstream chemistries. This because the high voltage fragmentation can allow a better physical sorting and easier disassembly and lamination of the component, with an easier access to more materials with higher purity, and this make this technology well adaptable to the direct recycling by separating the conductive foils from separators and plastic and concentrate high quality black mass. Another important advantage here is that this kind of technology can be customized on demand depending on the chemistry, and this again is a really added value that we can bring in the recycling research and technology more in general. The basic principle is to put directly the cell that's been, of course, sorted by the module in a water medium, for example, water, between 2 electrodes, and put a breakdown voltage, high voltage on of the water in order to achieve discharge to the solid samples, resulting in the selective breakage of the single component of such mixed materials or composite materials. And the results are there, because we are working on a failed cells coming from FAM, a big cell made by 30 layers in a pouch cells. And what you can see there is the separation that, of course, we need to still further optimize. Separator of plastics, the separators of the cells, the current collectors, and the concentration of black mass made by LFP and graphite dispersed in the wastewater here. And we are now at the level to characterize each fraction in order to also modulate the parameters on which the high voltage fragmentation is based on. Another important aspect for us is to recover the organic basic compounds in addition to the CAM. This because there are several positive aspects that we can exploit. For example, graphite, the fluorinated binders, and also the electrolytes. Starting from the PVDF, we know that it is a fluorinated polymer which has an important value from an economic point of view, but also is a potential source of PFAS emission, and also fluorine gases or hydrofluoric acid toxic compound that can be obtained especially during some hydrometallurgic approach. So it's important to investigate the possibility to recover this kind of polymer, and we are doing that by means of innovative approach, like, for example, supercritic fluid extraction. Then we are also going to recover the electrolyte because, again, there is some value there, but also because the carbonates composing the electrolyte are flammable, as we know, and the removal of the electrolyte can make safer the deactivation and the recycling of the battery during the following step. And finally, graphite, because to recover graphite can, of course, reduce the potential carbon footprint, the carbon footprint, but also graphite is a key component in a closed loop recycling system, so it can contribute to have higher revenue, even if graphite is not still considered in the battery regulation. This is just a first example on what we are doing to recover graphite by means of a greener froth flotation process, which means using greener frotter and collectors. And we are working on a real black mass coming from end-of-life batteries of electric buses. We are having very high recovery yields, higher than 19%, with a refining of the graphite very close to a potential battery grade, because we are now at a purity level exceeding 99.5%, with very good microstructure and also morphology that we are targeting by means of Raman spectroscopy, of course. So you can check here the order disorder properties of the graphite, but also the structural component and the microstructural order and crystallographic approach properties of the graphite. We are at the stage of the preliminary functional test because we are now comparing a fully recycled graphite with a commercial benchmark. And as you can see here, the results are really promising. Of course, we can add further improvement there, but in any case, we have a quite good capacity retention after 400 point cycle, of course, and a very good IC, which is in pretty nice agreement with the commercial systems. The electrolyte, how we are recovering it, we are working on end-of-life batteries, deeply aged batteries based on LFP with a state of charge lower than 50%. And we are extracting the electrolyte by means of SOX-select extraction, precipitation, the lithium salts, and we are also characterizing it, and purifying the solvents, the carbonates, by means of distillation approach, and checking by analytics if the carbonates may be reused in a battery remanufacturing process, or eventually, in case of low quality, to retransform it in more in added value materials, like, for example, valuable surfactants. What we are developing in Renovate is especially a protocol based on gas chromatography, mass spectroscopy, in order to easily and fast have the fingerprints of the carbonates we are recovering from the batteries, with advantage to have some beginning of life cells that can be used as baseline. And the important information here is that in case of deeply aged of end-of-life batteries, the carbonate appears really degraded with a high numbers of byproducts. So it's really difficult to think to recover the carbonates from end-of-life batteries and reusing them in a remanufacturing process, but we can find something to do with these low quality carbonates. And finally, just some inputs on the LFP direct recycling. We are just starting some important reconditioning process because, as Marcel well said before, it's not a question of recycling materials, but also make the recovered materials ready for reuse in a battery. And this, in case of LFP, is really important because, of course, as you know, there is a physiological lithium loss from the cathode because we are forming a solid electrolyte interface, and also the microstructure and morphology can change. And just think is to the carbon coating, for example. So we are developing here two types of reconditioning process. One, a dry route at low temperature in order to avoid any additional solvent, and another wet route based on recyclable redox coupled. Just a final feedback from the Renovate outcomes is again a work on LFP cathode from end-of-life batteries, but also from manufacturing scraps that we are recovering also by delamination through ultrasonic approach. What we are achieving here is that a very fast LEC correction and the restoring of the lithium stoichiometry, because as you can see in this table, the aged batteries has lost more or less half of the lithium content in the structure, that after the reconditioning process is fully restored. We can exclude, of course, thanks to a deep structural characterization by X-rays diffractometry, the presence of any iron lithium antisites defect that, as you know, they are really detrimental in the functional performance of such cathode. But an important information is that the reconditioning process we are proposing is capable to preserve the carbon coating around the LFP particles, as you can observe from this electron microscope image. So just a final information I would like to share with you is also to put effort on clustering action, which are very proactive under the umbrella of Battery 2030 Plus, but also it's important to communicate with other recycling projects coming from different platforms. So in particular, Renovate in the University of Pavia has some cross-fertilization activities with other European projects with higher TRL in order to get ready for a potential scaling up of the direct recycling technology we are proposing, because now it's important to try to boost and foster the scaling up of direct recycling. For example, Automat with the TRL7, when the focus is the advanced disassembly and sorting solution, we are trying to make stronger our digital platform. And also with BATMAS, with the i3 platform, with further higher TRL, which is employing the first European circular battery valley by deploying breakthrough green technology around 4 demo lighthouse. One of these is the recycling of batteries and the recovery and the reuse in a battery manufacturing process, where the important key players of the European battery value chain are partners, for example, Verkor and Orano Mining. So I think this was my last slide. Again, it was my big pleasure to be part of this great pool of speakers, and I really thank all of you for listening and for your kind attention. Thank you very much.
Thanks, Eliana. So we are going to go directly now to Andreas. Eliana, there's a couple very specific questions in the chat about things. Maybe you can take a look at those and put in a few answers. And Andy, I see that your slides are shared. I'm looking for you in the chat or in the list to highlight you. There you are.
Okay, can you hear me and can you see the screen in presentation mode? Okay, perfect. I'm also very happy to be here, and thank you for the kind introduction and also for the invitation. And I will give you an insight in the reuse project. So the reuse project is coordinated by my colleague Claudia Stauch from Fraunhofer ISC. And the reuse project is focusing on the recycling of direct recycling of LFP batteries. Okay. So the consortium is out of 13 partners from 7 European countries. So you can see here the logos and also a few companies which we heard in the morning session. So also Keyboards is involved, and Stena is in the advisory board together with Nielsen and Siemens. So for the reuse project, we have 4 main objectives. So the first one is the development of the discharge and also for the sorting of batteries. So when we have different kinds of batteries, we want to sort out the LFP batteries, then we can bring them in a direct recycling approach. We also develop an automatic disassembling robot system where we can open the LFP cells and separate anode and cathodes from each other and go to this direct recycling approach. And I think in the heart of the reuse project, we have our work package 3. So here we want to develop a specific direct recycling process path for a very efficient recycling of the LFP and also for the graphite. And we have also a huge work package for LCA and LCC. With this, we want to compare our new process for the LFP direct recycling with other processes in direct recycling and also in hydro and pyro processes. So when we look at the overall concept, so you see in the blue arrow the life of a battery from an active material, then to a cell, and then the battery usage, and then the battery collection. And in reuse, we want to close this loop, starting with the battery sorting, then the decharging, deactivation, then the automatic disassembly, and then the direct recycling of the active materials. So for graphite and LFP, want to use it again. And also we look at the other materials like the binder or carbon black and look how we can bring them also in a second use. So when we look in general for a direct recycling approach and we are focusing on production scrap, here we have also a very wide range of different scraps. So we have on the one hand the cathodes, then the anodes, and in these cathodes we have different active materials, we have different binders, we have different additives, also the same for the anodes, and then we have other electrodes or production scraps from solid state batteries or sodium ion batteries in the future. And there we see that there is not the one direct recycling process. So we have a lot of different methods, and each component and each additive will affect the direct recycling approach. And for reuse, we want to build up one specific path for the direct recycling of LFP. And we differ them in 4 main processes. So the first step is when we use electrodes, the coating detachment. The second part is the removal of the binder, that we can separate the active materials from carbon black and also can remove the binder. And then we go further to classify the materials and also to remove some impurities when we have something in the black mass. That we have the active materials and the carbon black and the binder separated and can bring them in a second use. And with the recycled LFP materials and graphite materials, we go to a regeneration process to bring in lithium again and to repair the structures. And the aim is that we get, so the first aim is to get out the cathode and anode materials for a direct reuse, and we also want to recover carbon black and binder for a second life. And as I mentioned, so what we see is that a lot of different methods for each process step, and we have to find efficient path for the recycling of LFP batteries, and for these batteries we are focusing in. And we want also to understand the influence of the different processes back to the influence of the regeneration and the performance of the active materials at the end. And the goal is to find a process with a low energy consumption, with a minimal use of chemicals, which we want to use processes which are scalable. And yes, the performance of the recycled material should be at the end like a fresh material. And when we look now in the reuse project, so it's the part of the work package 3, we start with the coating detachment, and here we see a very, very nice presentation from David in the morning. So the keyboards is one of the partner who is doing it, and they will do it with this aqueous process. And here you can see the different samples we generated. So this is, we call it recovered active materials and recovered cathode materials in different states. So in a dispersion and also in a powder. And we have them for different cells. So here we use the cells from Morrow batteries and 11E. So these are both part in the consortium. And in the future, we also want to use other delamination methods like solvent-based processes, and then a process from the startup Cell Circle. They will use a mechanical try process, and then we will compare these processes to each other. The second step is the binder removal. Here we start using solvents. So the first state-of-the-art process is the extraction of the binder with NMP. So yes, it's not the best way, and NMP is not the best solvent to use. But for a baseline, we use this. And for example, very, very promising solvent is TEP. So here you see in the pictures, we dissolve PVDF as a model system in TEP, and it dissolves very well. And then we get we put some water in it, and the PVDF precipitates, and we can centrifuge it and can separate it from the solution. And this process we want to bring in the real recovered cathode black mass and look if it also works in that. And in the future, we also want to use supercritical solvent systems that will be done by DTI from Copenhagen. The next step is the separation of the active materials. Here we are focusing on a centrifuge process. We use semi-continuous centrifuge. So when we have separated the anode and cathode, the active materials from the carbon black, we pump this dispersion in the centrifuge. And due to a difference of particle size and density, the LFP particles will remain in the centrifuge, and the smaller particles like carbon black will go out in the centrate, and so we can concentrate the LFP particles without impurities and go further to the regeneration process. And we also use a lot of aqueous-based processes. So we see that we have a lot of lithium in the process water. And here we have also some activities to recover lithium out of the process water. And here we develop some adsorber particles. We put them in the process water, and the adsorber particles absorb the lithium ions, and we can separate them by magnetic separation because they are magnetic particles, and then we have a washing solution and desorb these particles. Then we can use it again and do it in a circle. And we see that it's a strong dependency on the pH value. And you see in this measurement that we can separate more than 70% of the lithium particles at a pH value of 9. And the last part is then the regeneration process. So here cannot show some results at the moment because they are not published yet. But in principle, here the partner Vito is responsible for the cathode regeneration together with 11Es, and they use the LFP particles in the regeneration of the particles with a microwave system. They put lithium salts in it and reducing agents and make a synthesis via microwave, and then we get out the relithiated LFP. And for the anode side, there is AMPA responsible for the regeneration, and all this results we can demonstrate soon. Yes, so the last step is that we will validate the materials in real cells. So here we have our cell manufacturers, 11Es and Morrow batteries, and we have also look for the other components here. For example, there is Arkema Evolve, who will look if the PVDF can be used again, and what we can do with these materials. So this is more or less a very easy way for the recycling of a production scrap. But when we go to end-of-life batteries, it will become more complex, because we have first to sort the cells to get to separate, for example, NMC batteries from LFP batteries. Then we have to open the cells, and we have to separate the cell components from each other. Another approach is also that we go in a classical mechanical process, which is used mainly for hydro processes. So we shred the cells and get a real black mass with anode and cathode materials, and look if we can use these approaches we have in this direct recycling process and separate or concentrate the active materials. And yes, we get a lot of new challenges for the end-of-life batteries, so we need this further steps. We have also aged materials. Then we have some SEIs or CEIs on the surface. We have to clean them. We have a different state of charges which affects, for example, the coating detachment, and we have more impurities in the black masses. And we also want to look if it's possible to use this black mass from a mechanical process. I have a few examples for the first one. So we have a scope defining the waste, which waste we have. And here we classify between wet waste, so it was the liquid waste, and also the wasted batteries. And then the dry one is more or less the electrodes in the battery cases. And then we have the black mass. And there it's not so easy to transport it from one partner to each other. So that's one of the main topics. Is it a waste or is it a product? And this we have to clarify. And the second thing is the sorting. Here we use, it's done by the partners Vito and Sorbart from Belgium. Here we scan the cells via X-ray, and via AI-based sorting mechanism, we can detect the elements and can separate the LFP cells from the other batteries. For the cell opening at Fraunhofer, we built up a system with the opening by a robot. So you've seen that the process from keyboards, it's a little bit similar. The difference is that we use a robot which can see different type, or can detect different type of cells, and via a camera, and then we know the dimensions, and the robot will do everything. So the robot can open the cell, can separate the cells, and as a result, we get the separated anode, cathodes, the casing, and the separator. So we've done this process in a lab and do it by hands, and now at the moment we transfer it to the robot system. And another part is the shredding. So there are a lot of shredders, but it's not so easy to get a small shredder to make some investigations on it. And here the DTI from Copenhagen has developed a very slow, very small shredder, where we can make different conditions and use commercial cells to get out the black mass, and then we can use it and transfer it in work package 3 for a direct recycling process. And when we look at the end at the overall concept, I've showed you some results. So this is the overall concept. reuse project, and then we want to bring all the different product waste streams together with a production scrap from Morrow and 11Es, then cells from keyboards, then the sorted cells from Vito, and we want to bring everything together, and all the project is we want to make all this LCA things to look which is the best way for the recycling of the different waste streams. And at the end, we've made a conference last year in Würzburg regarding the direct recycling, and we were very, very happy that so many people came to Würzburg. There were more than 160 participants and a lot of presentation and posters, and there was a very, very nice community which grows up. And I'm very happy to invite you to the next direct recycling conference. So the planning is started right now, and we will do it at between the 3rd of February and the 5th of February next year in Würzburg, and we will share more details soon. We will be very happy that we can see a lot of you in Würzburg next year at the conference. And with this, I want to end up my talk, and thank you very much.
Okay, thank you very much, Andy. So we have, I think, a few minutes. Let me just check the schedule. Oh no, we're already into our break. So I'm going to say we will come back and meet again at about 11:50. So we'll give you 5 minutes back of the break. We'll start again at 11:50 with the panel discussion. And there we will have all of our speakers. I will chair the session. We have some questions already prepared for our speakers, but also if there's other questions from you in the audience, we would be happy to address some of those as well. So we will be back at 11:50 live. Thanks. See you then.
You know why?
So I hope people are slowly coming back from our short coffee break. And for the speakers, when you're back, if you want to just switch on your cameras and then I know you're there. Hi, Liana. And Andy and Marcel. So we'll see. I would expect that Arne will be back in a little bit or shortly. I know David, as he mentioned, has his visit, but he wanted to try to join us for the panel discussion. So we'll see if he joins us in the next little bit. But I would say we get started with our two project representatives and Marcel, and we can already start with some of the things that we were hoping to discuss. So maybe we heard from David and Anna some of the challenges that are facing them as battery recyclers. Maybe then I'll direct this one to you, Andy and Eliana. From the more research perspective, from the more, let's say, academic or applied research perspective, what do you see as the most significant challenges that we're facing in terms of battery recycling?
I can start, or Andreas? Okay.
Yes, go ahead, Eliana.
From the scientific point of view, in my opinion, one problem is the complexity in the design variability of batteries. A complex design, two varying chemistries, and also a still lacking standardization of the recycling process. Of course, when you have to manage different chemistry, this could also require for advanced dismantling and also sorting the technology. And in this case, I convinced that science can ramp up the technology, because we still need, and we can basically to provide, to improve the pretreatment mechanisms, which are really important for the management of different chemistries. And another problem I see also regarding the chemistries that can somehow solved by a design for recycling approach is the difficulties that the batteries more or less have in terms of opening of the cells, because there is a great problem for what concerns the structural adhesives, so that the modules are also often difficult to open. And finally, another challenge, I think, also concern the quality of the black mass, that somehow is still too low, because we are receiving in my lab different types of black mass coming from different recycling plants, also from Indian companies. And the impurity levels coming from the current collector is really too high to manage the recovery process of materials. This especially in case of direct recycling approach. Also in case of hydrometallurgy, because aluminum and copper are not so easy and they are tricky to be separated for the critical raw materials, but this could be a problem also in case of direct recycling. This is just a view from a scientific and academic point of view, of course. So.
And to add, for example, so I totally agree with you. So one thing is that I think it was a picture from Arne with the cell to pack and all this adhesives or this this materials between the cells is so hard to get out of the cells that you can separate the cells from each other. It's also a very crucial point to build up a secondary energy storage systems. So here we have to look at design for recyclers that we can separate the cells with, for example, triggable materials that we can separate it. And also when we look at the, as you said, Eliana, so when we have black mass, so we have a shredding process, we have the impurities, and when we go with this opening of cells, it's very complex, and we have different layouts and so on and so on. So it's a very variety of different cells we have. And when then we look at the direct recycling approach for the electrodes, so here's the binder, the most critical point. So here we have this fluorinated binders, and it's very tricky to remove this binder. So here we need some solvents which are critical or which are expensive, and this step is one of the crucial steps in the direct recycling approach. So here also we have to look at a design for circularity to use other binders. For example, when we recycle production scrap, the shortest way is to remove the layer and use it directly again. But with this binder, which are at the moment on the market, it's not possible. So here, I think it will be a huge challenge for research also to develop new binder which we can, on the one hand, remove from the recycling process, or we can use it directly again. And I think that's one of the most crucial point. And here we also need the acceptance of the cell manufacturers and the OEMs. That's also a critical point.
Yeah. Yes, the managers of the fluorine-based compounds is also open in an open debate, also in case of fuel cells, for example, because we have also fluorinated polymers in case of fuel cells and electrolytes, and there is an open debate on how to understand the mechanism of degradation of the fluorinated binders or polymer membrane in that case. Also because there is still a lacking protocols on how to understand the potential emission of PFAS coming from this kind of materials, and also how to measure the total organic fluorine that you can find in a black mass or also coming from the binder. So this, in my opinion, is a really nice field to explore. And where science and research can, of course, contribute in a longer term research, of course.
And also we have to keep in mind the tri-process cathodes, which are we have a PTFE as binder, so that's the next challenge for the recycling approach, to remove this kind of binder. And also here we can also look in design for circularity, which binders we can use for also tri-processing.
Exactly. And there is a call now in the clean hydrogen partnership where the PFAS emission and how to manage the fluorinated polymers should be done. So it's a really hot topic, and this it could be a matter also of cross fertilization between different technology, batteries, fuel cells, for example, because this is a common problem for both the technologies.
Marcel, would you like to comment as well?
Yeah, I fully agree with the technical challenges, but let me add a market challenge that we discussed this morning. Remember the slowdown of the EV market development? It is really a challenge now to match recycling capacities with this market weakening. I believe that there are about 30 recycling projects that have been announced or that are being built, but due to availability of material and financial support, I believe almost half of the capacity announced is either on hold or not certain to go ahead. So there is a market issue. Another challenge that I see is the high cost and the complexity of the recycling. The current recovery recycling targets are 70%. So that leaves still a lot of valuable materials that are unutilized. And maybe another challenge in all the recycling processes is the high energy intensive character of the recycling, high energy consumption, and maybe safety risks as well that are inherent to recycling processes.
So we've talked now quite a bit about challenges and things that have to be overcome. Nonetheless, there certainly seems to be a lot of positives and a lot of opportunities here. So there's been a lot of discussion recently about European competitiveness. So what do you see in terms of opportunities? Particularly, does a strong battery recycling industry provide opportunities for the European value chain? And what do you see in terms of the developments coming in the next few years? What do you see, let's say, when we look at battery recycling in 5 years? What will it look like? Is the slowdown going to be a major problem, as you mentioned, Marcel? Or is there a way for the companies to manage this?
I believe personally that there is still a lot of work to be done in the logistics for the next years. Talking about collection, transportation, ADR issues, sorting, disassembly, pre-processing. So the initial phase of the recycling chain has to be further optimized. But positive points in the coming years, I believe, is the introduction of new technologies like digital twins, blockchain, AI, that can help to improve battery recycling, tracking materials across their full life cycle, and enabling in the future digital product passports. I also believe that for the coming years, Second Life could be, if the economics are right, could be a major opportunity. And as we discussed this morning, direct recycling is also key for the future. And maybe the extended producer responsibility that is coming, that exists, will also have a strong impact. So there is positive effects with new technologies appearing in the recycling chain.
Anna, I see you're back in the group now. I'm going to spotlight you, and if you want to comment, you're more than welcome to.
Thanks, Gwen. Yeah, I joined a bit late. Sorry for that. I was
No
on a call.
problem. Did you hear the question?
Yeah, I heard the question, and I'm back for the last 10 minutes ish. So I've been listening in. So I think there's a lot of opportunity to be had, especially for young people looking to have an exciting job. And why is that? Because I see we have built a 30 million euro shredder. We've put a team of 2-3 engineers on it, and we found out, oh shit, this is so hard to really understand. And you can see it along the lines of the questions. I mean, there's different binders, different electrolyte solvent systems that we find, and those things mix up and create things that we didn't anticipate at different temperatures and pressures. And we struggle to understand because we didn't hire battery engineers and battery scientists. We hired, or we used what we had, our guys that know mechanical sorting and recycling. And we were overwhelmed by the new challenges, and we needed a lot of help. And we got it from the suppliers but also the suppliers are working with mechanical engineers mostly. So there's a lot, in the chemistry and in the thermodynamics happening that we really struggle with, and people like me have no clue about. We just see the outcome, and we think, okay, yeah, there's a lot to improve. If you read in the chat, you will see one of those examples. So also, that's maybe not for scientists. That's more for like the real practical recycling. There's a lot of manual work with the discharge. And I think discharge will win, not the submerged discharge like in Asia, the manual discharge where you connect two electrodes, the two electrodes to a electronic load and take out the energy and use it somehow, but take it out. I did that a few times with my colleagues, and that's very time-consuming manual work actually. But it's also quite satisfying to see the energy come out and then to see that you have made this previously unsafe battery safe. But if you scale that to the needs of the future of batteries to be dismantled and discharged, and see that these robots that open the packs, they can open like 1, 2, 3, 4, 5 different packs. And then seeing that some of the screws are corroded, so we take a hand drill and drill it out because the screw doesn't, you turn it, but it breaks and it's still stuck, and things like this. There's still a lot of manual work needed. So a lot of people will be absorbed into this industry. So I'm, for the people side and for the labor market, this is actually quite good news as one example. So I'll stop there.
You're muted, Gwen.
You muted?
You're muted, Gwen.
Oh, sorry. I muted so that I didn't hear any other noise. So this is interesting, Anna, about the people. Does this mean that also for the education side, the battery scientists that we're educating at the various universities and so on, that you're going to be looking also for people with these specialties?
Absolutely. I think it's one reason why I wanted to come here is to, promote Stena as a viable employer, because just for you to see that there's the plant coming up in Italy. I don't know how big it's going to be. I don't know when it's going to be, and it's going to be a first treatment plant. We hired a technician directly from the university in Poland to start we call that battery center, where we start taking in batteries and start dismantling, discharging, and then you become a business person because you run a plant. Suddenly you get 2 co-workers that you have to, but you are the person they go to when there's an issue, when there's an electrochemical issue. Why is it getting warm when I do this? And you have real life, quite small problems to solve suddenly, but you start applying your knowledge in a very broad application field. And social things become important as well. But we see that the recycling industry of the past, it usually has a lot of hands-on technicians like fitters and mechanics as the leaders in these positions. And we are transitioning in the battery field in the recycling. It's too complicated. We need university graduates to fill these roles. But they're, more of 50% of the time is not very scientific then in this work. It's really leading a team and making this, motivating people and making this work, but knowing when there's a problem, what to do.
I think that's very positive for all of the young people that we're working on educating at the moment. Maybe we circle back to the question of the positives. What do you see are the opportunities? And Eliana and Andy, if you want to comment.
Yeah, I would add that we have in Europe strong skills and know-how in the recycling technology coming from mining. So we have already high recovery yield for some materials and so on. I think that we can also make the difference with respect to the China or other competing countries in terms of sustainability, because also there we have great know-how. For example, the task force on sustainability in our community. And I think that this could be really the difficult, not only in the state-of-the-art technology, but also in the forthcoming technology, as mentioned by Marcel before, that we have that they already have great potential. For example, also pyrometallurgic that can somehow lead the transition towards a new technology. There is a lot of improvement in terms of sustainability there that has been discussed and demonstrated by several scientific papers. So I think that sustainability is where Europe can greatly contribute to the improvement and the implementation of recycling and the battery value chain. in my opinion.
I think as what Marcel said, so the connection between the battery pass and all this digital platform, I think it's very important to bring it in a circle. That also the recycling is one of a main topic, that we can use all the knowledge we have from this battery pass and to bring it into the recycling process, and then we can have a tool where we can decide which recycling process is the best for each product waste. So is it feasible to go here in direct recycling, or go in hydro, or go in pyro? So I think it's very important. Then we don't need all this sorting technologies and so on. So we can reduce the processes and have everything in this digital world. And also a big opportunity when we look at the direct recycling approaches is that we have a very strong industry for machine producers here in Germany or in all over Europe. But I think there are so many interesting companies, but they don't know that they have good machines for the recycling. So our aim is a little bit to bring them in this recycling world for direct recycling, and use their machines to show them that the machine is running very well for the recycling process. Because as Arne said, the recycling and also the battery industry, or the battery materials are very difficult. So we have NMC, which is toxic. We have this HF formation and so on and so on. So that the manufacturers cannot validate their machine for this process. They need some universities or research institutes which know what they are doing and make this process or make this validation for them. And there we have a very large portfolio where a lot of different machine suppliers are here in Europe. So I think that's a very big challenge also for them.
So thank you all. One of the things that always kind of strikes me when we start talking about batteries and markets is you're seeing, especially in the Asian markets, this huge vertical integration. So you see the raw materials, they have taken control of these around the world and things like that. With all of the use of batteries in Europe, we have this huge pool of raw materials. So what do you think needs to be done to keep these raw materials in Europe? Can we keep them in Europe? Is it going to be profitable for companies to keep them in Europe? And does this give us a way to basically have a feedstock for the battery production industry? Who would like to start?
I have a quite pessimistic view on this. I will start not being optimistic now. We see that the industry, the production of batteries, and it needs a PCAM stage, is in China and some of Asia, but mostly in China. And we see that the black mass is flowing there. So we know that CNGR, for example, is building the first PCAM for Europe. They wanted to build it in Finland. Now they have it for Europe, but in Morocco. There is some European actors that want to put this into Europe, but they really struggle because the energy intensity of this process is really high. And they look for cheap energy. They look for cheap workers as well, but mainly cheap energy. And this is the process that, I mean, where you have that region will get the final salt for CAM production that can be used in a new battery. And for now, I think more than 90% of the world's PCAM is somewhere in Asia, and then the CAM for that makes sense to have in Asia as well. And actually what we see now, a company like LGES in Poland or CATL in Germany, they get their CAM produced for them in South Korea and China, not in Europe. So they get a finished CAM product that they coat, or maybe even they get a finished cathode foil, but they get the products from Asia. They don't get it from Europe. And that will stay for a long time with the current energy cost situation. Also, investment cost is much higher, and a lot of different things are worse than in other places of the world in this PCAM and CAM stages. And we saw Northvolt trying to establish it. Stena is one of the investors in Northvolt and has also been the biggest recycler for North Volt material. They tried to put a PCAM up and a CAM production. They called it upstream up in Skellefteå in Sweden. And that did not work according to plan, at least, and economically. So they are, I mean, you know that they are in a bankruptcy proceeding, and it doesn't look so good. So yeah, a big struggle. And I don't see, even if we had the production of PCAM and CAM in Europe, we are like, the feedstock that we have in recycling is currently so much less than the need of new batteries that we will struggle even. I mean, what are these targets? We had them 60% cobalt and then 26 as the higher end that Marcel showed earlier. We will struggle to, absolutely struggle, at least in Europe, to get this done in 2031 and 2036 when it's time to get these targets in line. We will probably achieve it if we, and that's also a struggle, but if we take the CAM material from Asia, where there is more feedstock of recycled material, because the European American goes there and they have their own being the biggest, they might be able to supply just enough to fulfill the European legislation when we import it from China. But European recycled material will probably be too low volume, even if we had the means to recycle it. So there's a lot to develop. And I mean, cheap energy might be the key here. Sorry for the long.
No, it's great to see the insights.
Yeah.
Did you want to comment, Marcel?
But I fully agree with Arne, but I believe we should, in Europe, put more focus on sustainability, low carbon footprint. We should also try to integrate the value chain, have an integrated approach in the value chain. We should be champions in innovation, and we should, more than the Asians, encourage, I come back again to that one, to reuse and to second life. I know that second life is not easy, but and it is confronted with economic issues, but it is part of circular economy.
So, Andy, earlier you talked on, or moved a little bit in this direction of design to circularity. And there was also your pictures, Arne, of opening the packs. And Andy also mentioned the adhesives and things like this. Are there specific design for circularity things that would significantly help? What about standardization? I know there has to be an acceptance level, as you mentioned, Andy, by the end users and the OEMs. But is there also potential here? What specifically would help? Or what else can we look at?
Can be a bit optimistic again. Thank you. If I jump in here, there's one thing that every recycler wants. If you get a cell to pack or a cell to chassis pack, we want an adapter that we can usually buy from the OEM of the pack to slap on from the outside before opening and getting our people's hands into high voltage. That has and talks a kind of a recycler protocol, so that when we connect our electronic load, we can discharge the pack from the outside, not going into this very unsecure area of, you know, when we start using a disc saw or an angle grinder, or how we want to call it, on a pack, that it doesn't feel good. But we have to. This is the way today, and we are trying out water cutting and laser cutting. But today we use this, you know, and that introduces a lot of heat and, you know, little flying sparks. It doesn't feel comfortable to do that on an 800 volt system that you get. So if we could discharge it before, the cells will be much, I mean, the energy inside that could combust is so much lower, and it's so much safer if we could do that. And we have asked that and said that on every conference we go to, that we want that, and we haven't got it yet. So if you could promote that for us, that would be fantastic. because we know it's the car can do that. You connect the car, right, and the CAN bus talks and it says give me energy, and the car gets the energy from the battery. So we just need discharge. We don't want all the other parameters, but just discharge. We don't want to steal away all the information that is so precious that's in the battery. So we don't need full access.
Marcel, Andy?
Yes,
Eliana?
I think that's a critical point, that this information. So I think it's also a problem in the battery pass, which information has the companies or the suppliers have to put in the battery pass, and which information get the recycler and which information need the recycler. I think that's a very, very critical point in this part. So also the connecting and get the information, and also when we look at this cell to pack, I think so. When we look optimistic that we can have adhesive between the cells that we can trigger, or we know how we can remove this adhesive, that we can get out the cells, and then in the other optimistic way we have a very smart diagnostic tool that we can separate the cells and sort them in working, not working, or classify them and put them in second use or in recycling. I think that's in an ideal world. I think that would be very nice, but there's a long way to this.
Yeah, but design for circularity also includes features that enable actions to prolong first life of batteries. And coming back to reuse, repair, refurbish, remanufacture, and aspects that could help into that one is what we do in Battery 2030 Plus, continuous improvements in sensors, methods of detection, improved battery management systems. They are crucial to provide state of health determination for individual cells, to enable, in fact, a total design for circularity in the battery system, especially for LFP batteries.
So I'd also like to remind the audience, if you have questions, please let us know. Please put them in the chat. If you would like at the moment, we would also have the opportunity to actually ask a couple questions. So in the group, while I'm waiting to see if there's going to be questions or hands coming. So I think it was, I don't remember now, Marcel or David, one of the two. You saw this long-term, short-term business development. So let's say looking at scrap, looking at end of life. How do you see this develop? Scrap is going to be the short term, yes. At what point are we going to really get a big jump with the way batteries are changing or with new chemistries? In terms of end of life, I mean.
On scrap rates, it's clear that at beginning of a battery production line, scraps are high. Scrap rates are high.
Yeah.
It can be up to 30% when the production starts. But we are now moving into more well-established production lines, and scraps are reduced to 5 to 10% today, I believe. And
Correct.
that is, for instance, shown already in Asia. That scraps rate reduction is made possible by digitalization, automatization. But yeah, we need scraps for the moment, and scraps will stay the main source of feed up to 2030, I believe. So we are heavily depending still on scraps, manufacturing scraps.
I agree.
Yeah, I have a question to Arne. So, when we get is this production scrap on the market? In my feeling, all the cell manufacturers or cell manufacturers, there's a great know-how in this cathode and anode materials, I think. So in my feeling, they want to recycle it on their own or have exclusive partners or something like that. Is this this production scrap? Is this on the market or not?
Yeah, it's on the market. I can comment on the European cell manufacturers. Not so many. Starting with Northvolt, then you have a little bit Freyr started and ended, kind of suspended in Norway. Morrow starting now. CATL having started. I'm not so aware of the plans of who's built that in Hungary. Not sure. And then the LG in Poland. All of them are tendering their waste. You can not sure if you're familiar how a car OEM or a car supplier manages their waste. If they have a valuable waste that they want to get rid of, they tender it in an online platform, and then they invite who they think could take it. So you must make yourself aware as a recycler. But if you have done that, if you have been to the conferences, fairs, and you have made yourself aware, wave your flag, they will invite you, and then you basically describe your processes, you answer all the questions, and then you place a bid. Usually, actually, it's kind of an Excel file where they can easily compare you. And then usually best price wins. So if you tick all the marks, that is. And so as far as I know, everyone in Europe is tendering this in Europe. But seeing the prices that they get in Europe, they have a strong urge to pull their CATL, for example, they have Brump as their own internal recycler in China. Brump is not in Europe yet. So they have an urge to pull Brump over to get them into Europe to recycle for them, because they believe that then they will have a better economy in recycling. But then also Brump will be faced with the European legislation and a lot of things that are a bit more complicated in Europe. So it's not clear for them if that actually is an advantage. But yeah, it's actually completely accessible. It will be really hard to access for a research institution or for someone not doing it in an industrial scale and commercially. And because you compete on high volume and low price. So it's a bit different than if you have a car dealership that takes out 5 batteries a year from electric cars and otherwise is, dismantling cars or so. There you have good access. They talk to everyone, and you don't need to be invited.
Sorry, I was so interested in the answer, I lost my train of thought of what what I wanted to ask. I think it was something along the lines of new chemistries, and that most of our discussion and most of our focus has been on CAMs, so cathode active materials. When we think of new chemistries, we're seeing a shift for the anodes from graphite to graphite silicon composites. Of course, this is adding a layer of complexity. We're talking about sodium ion and commercialization of sodium ion. Okay, LFP is probably eating into that market a little bit. But where do we see this going? What does somebody want to comment on the anodes or on maybe new chemistries?
Yeah, I can tell something. The new chemistries are really interesting from a scientific point of view, also crucial in terms of recycling, because, for example, if we think, for example, to the lithium metal batteries, there is a big issue on the recycling of lithium, because this can require a change in the recycling approach, the recycling plant, because lithium should be managed in a different way, even if something is starting, because there is an innovation fund from New Solution that is calling for the recycling of lithium metal. So we are just talking about a new generation of lithium. And regarding the anode, there is an open debate, because it's not so clear what can be done in terms of materials at anode, because graphite is still unknown if it is feasible to use a secondary material instead of the virgin one from an economic point of view. And this is further complicated if silicon is present in the mixture of the anode materials, because it's really difficult to separate silicon from graphites. So this is just a further matter of research, of course, at low TRL at the moment, but this is, of course, something that we should consider because the generation 3B, for example, is very close to the market. So it's something that we need to consider very soon.
A positive point maybe is that in the work program of the Commission with the battery partnership, there is a call that is prepared on direct recycling for new chemistries. Work program 26-27. So the new chemistries are within the focus of the Commission with direct recycling processes.
So I see there's a question from Pushpendra in the chat. I think this is actually a good wrap-up question for our panel. There's been a lot of talk. I hope it's okay if I kind of put it in my own words. There's been a lot of talk of different recycling processes, lots of different chemistries, binders, things that make sense from a sustainability point of view. How do you see the future looking? Is it going to be a mixture, a balance of different recycling processes to basically optimize the best? Or do you think there's going to be one universal process that can handle everything? Who would like to take this?
I think
So,
Arne.
Andy, no, go ahead.
No. So
Then-
my research opinion is that we need different methods. So for production scrap, I see clearly the direct recycling, and also for low-cost chemistries, it has a potential. But we also need robust processes for EVs, for NMC. So that's the hydro process. I think it's very or more or less the best way. And when we also look at all the consumer batteries, so everything which is in the small devices. So here we don't know which chemistry is inside and how can we disassemble all these things and get out the batteries. So I think here's also the pyro process a very good option to recycle and to get out the elements what are inside. So I clearly see that we need different methods, different recycling methods, and I think because we have so much different chemistries and so on, so one universal big process, I think it's not feasible. But I want to learn what Arne say. So please go ahead.
Totally agree. Just expanding a little bit. If you look at other waste streams in the past, it came from putting on a landfill, then to thermal recycling, incinerating everything, getting rid of it. And then it went into different processes. Let's call them mechanical, chemical, thermal processes, mixtures of those, and they get diversified over time. And if you look at the amount of battery recycling patents being announced and research papers written, it's getting more and more, and different approaches, different solvents in hydrometallurgy, for example, specialized to different chemistries. But even in look at me, being half an engineer and more of an economics guy, even I do understand that there is a field where this submerged shredding, I don't really like it, because in a submerged shredder you can throw everything in and it gets mixed up and it's getting wet, and black mass that is wet is actually an economic problem. But it has a good application for the current version of cell to pack. We can't safely dismantle them yet, so why not throw it all into the big blender and get rid of it? But we have to find a better way for the future. So I call it the life cycle approach. It's quite nice to have this, and they try this, but I think in the end, the costs for that high wear and tear and then cleaning up the water is a nightmare, because it's super contaminated. The costs will chase them down and eat them up when they need to compete in the market, and then opening techniques will win in cell to pack long term. So it will be more and more and more, and the little niches startups will come. And you have seen, maybe you've read about To Zero, for example, having a novel approach. Then you have Scilib companies that are scaling up now, and for hydromet approaches that are a little bit different. And there's for sure a lot of companies that I've just missed that have really interesting approaches, and I think they all have their niche because they specialize on a very specific problem. And the batteries bring, I mean, the volume is coming, but they bring already now all these problems because we have a huge mix of chemistries. Maybe I can end with an example from my former life. We used to treat, if you know refrigerators, they had CFC foaming, and now they have pentane foaming. So what did we do when the CFC ended or was phased out? In recycling, it takes like 20 to 30 years until you will see the CFC phasing out. So get refrigerators now is maybe 80% is pentane, 20% is still CFC. And you had the mixed approach for those years. So the plant constructors, they built mixed plants, but when you got to 50% input pentane, those mixed plants were economically unviable because you had to do so much explosion protection, because the pentane with the ambient air and then a shredder, it's an exploding atmosphere. So the first plants that came in spread it up and said, we separate it. We have a robot testing the foam. It splits CFC in one side and pentane on the other. Those were just, for the pentane, they just had a huge volume of extraction of air. They never got to the lower explosion limit of pentane. They never got this explosion problem, a lot of less safety things needed, and they just incinerated the pentane, generated some heat on the outside. And they were economically much better, and they are the future of recycling of refrigerators. And they just kept the old line single for CFC, even though the old line could take both parts. So out of one size fits all, they made two, and they were economically better. And I think this will happen for batteries more and more and more, that we will see so many different recycling routes, and reuse being, or the reuse project, the direct recycling being one of the most promising from a viewpoint today.
So on that, I would like to end our panel discussion. I would like to thank Arne, Eliana, Andy, and Marcel for giving us lots of insights. I hope this has been inspiring for our young scientists, especially. We're looking forward to seeing you back in the afternoon. As Arne mentioned, there definitely is a market here for young scientists and people who want to go into the battery field from the perspective of recycling. So this is a really positive, and so let's use the afternoon to find a way to help come up with some new ideas and have some fun. So Sylvia, do you want to add anything?
No, just that we will meet again at 1:30 p.m. and the link will be the same. So I will stop recording now, and I will welcome you again in the afternoon, in particular the young people who will be then shared in different rooms, and something is already organized. So thank you very much to all speakers. It was great to have you here, and in particular your very nice presentations. This workshop will be uploaded on Battery 2030 website, as we did for the previous one, and accessible to everyone, in particular to get better educated people for next future. So this is also in the frame of activities on education in Battery 2030, and not only. Thank you really again, and see you later.
Okay, thank you.
Thanks.
Thank you.
You.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.